In this video, I'm going to tell you about a trick using which you can find moment of inertia of certain objects using parallel axis theorem. And to learn about that trick, I'm going to use one example first and then we'll apply on certain objects. Take for instance, this is a rod of mass m and length L, and its moment of inertia, suppose we have to find about an axis through its center and perpendicular to the rod. We know that xi is, moment of inertia is some constant which we do not know yet, which we have to find, into mass of rod into L square. This is for sure. This much at least we know, that I will be, moment of inertia will be some constant into mass into L square. Okay. This mass can be written as lambda into length of rod, where lambda is mass per unit length, and this comes out like this. So moment of inertia is proportional to L cube for constant lambda. So if we have many rods and they have same lambda, then we can say moment of inertia is proportional to L cube. Now take another rod and having same lambda, but its length is half of the length of this rod, so it is L by 2, and suppose the axis again goes through its center, so that whatever the formula is applicable here will be applicable to this rod as well. Therefore, using the same formula for this rod, and since its length is halved, mass is also halved because lambda is same, we can say that moment of inertia of this rod, if it was I0, then for this rod it will be I0 by 8, L cube. So it is L by 2 whole cube, so 2 cube, that will make 8. Okay. Now moment of inertia about this point, about this axis, if the axis is shifted from here to here, will be suppose I, where I will be equal to I0 by 8 plus parallel axis theorem, use parallel axis theorem, m by 2 into L by 4 square. L by 4 is the amount of shifting. So this length is L by 2, half of which is L by 4. And this will come out I0 by 8 plus ml square by 32. Now, so we have found moment of inertia about this point of this rod. Now you can check that this rod and this axis is nothing but this half rod and this axis. So these two are exactly same thing. So it means the moment of inertia which we have found I here is actually half of the moment of inertia of this original rod, because the two parts have equal contribution in making I, the total moment of inertia, which was I0. So half of rod will make I0 by 2. So therefore this I should be equal to I0 by 2. And if you solve for I0, it will get ml square by 12. So this is the trick. We have used the scaling by which we got this 8. This was the effect of scaling, that length reduced to half, so L cube will reduce to 1/8. And we used parallel axis theorem here, and we reached to this point. The axis now reaches here, and then by comparing, or we could have done one more thing. We could have taken another half part, and same I would come about this axis, again the same rod, and then if we add these two, it will make this full rod. So this full rod will be made if we add these two parts, and these axes will come at the center. So exactly this situation will be arrived, and therefore the total moment of inertia I0 here is actually 2 times the moment of inertia I. So either use this method or use this, they're equivalent, the same thing. Okay. Suppose we have a square of side A, and we have to find moment of inertia about center, about an axis through center and perpendicular to the plane of square. Now divide this square into 4 equal parts and each part will again be a square of side A by 2. Now here again moment of inertia will be some constant into mass into length square, length is A. This is for sure. At least this much we know. It will come out of this form only, and C we do not know the value of C. Okay. And it is C into mass is sigma into L square, sigma into area into A square. So mass of this square is sigma into area, and area is again A square. So in all it is coming out equal to C sigma A4. So it is proportional to A4 here. So moment of inertia about an axis through center perpendicular to the plane is some constant sigma A4. Now apply this formula to this square. So moment of inertia of this square about its center, about an axis through its center perpendicular to the plane will be of this form, and this moment of inertia will be equal to C sigma, and instead of A we'll have to use A by 2 raised by 4. So if this was I0, this would come out I0 by 16. So this is moment of inertia of this square about this axis. Now shift this axis from this position to this position. So if this distance is r, so moment of inertia about this axis will be I0 by 16, this value, plus its mass, which is m by 4, into this distance square. And this distance you can check is 1/4 of the total diagonal. So total diagonal is a root 2, this is 1/4 of that. So a root 2 by 4 square. So this is the moment of inertia of one small square about this axis. Similarly, the moment of inertia due to 3 other parts will also be exactly same about this axis. So total moment of inertia, which was I0, would be 4 times the moment of inertia of one sub part. So we have 4 subparts here. So one subpart is making this much of I. So 4 subparts will make 4 times. So we have to solve this for I0, and if you do this, if you solve this, you'll get I0 equal to ma square by 6. This you can solve and check. This is the value of I0 you'll get. Okay. You can find moment of inertia of a body using this method if its subparts are of same shape. So this is the requirement. Suppose we apply this method to a rectangle of side A and B, and suppose the axis is again perpendicular to the figure and passing through its center. Now again divide this into 4 equal parts. Each subpart is of same shape, and suppose moment of inertia of this total rectangular plate is I0, then moment of inertia of one subpart about its center will be I0 by 16. Then shift this axis from this position to this position. So it will be I0 by 16 plus mass of this subpart, which will be 1/4 of total mass, into this shifting square, and this shifting is actually 1/4 of the total diagonal length. So that is under root a square plus b square by 4, it's a square. So on solving this, we'll get I0 minus I0 by 4 is equal to m into a square plus b square by 16. Then 3 I0 by 4 will be equal to m a square plus b square by 16. And then you'll get I0 equal to m a square plus b square by 12. So this is moment of inertia about this axis of this rectangular plate. If it was a square, then a and b would be same. Then you can write 2a square, then 2 will cancel this 12 and you'll get 6 here as we obtained earlier. Okay. Now I'm taking an example of an equilateral triangle of side A, and this is the center of this triangle, and we have to find moment of inertia of this triangular plate about an axis passing through center perpendicular to it. Okay. Now again, what we can do, we have to divide this into subparts such that each subpart is again an equilateral triangle. For that, divide this into two parts, a by 2 each, similarly this and this, and then join these points. So now we are having 1, 2, 3, 4 subtriangles of a by 2 each, of side a by 2, and each triangle is an equilateral triangle. So the total moment of inertia, which was I0, suppose, is equal to, okay, now first you consider this triangle. So moment of inertia of this triangle about its center, somewhere here, will be I0 by 16, using the same logic which we used earlier. And then we have to shift from our axis from this position to this position, because we have to find moment of inertia of each subpart about this axis only, and then we'll have to add. Okay, suppose this distance is r, then we have to add m by 4 into r square, and this we have to do for all these three triangles. Exactly the same thing we'll have to do, and plus this triangle is left. The center of this triangle happens to be at the center of this total triangle, so we do not have to use parallel axis theorem for this triangle. So its contribution is simply I0 by 4, I0 by 16, sorry. So we have to solve this to get I0, and again we have to find R also. If a triangle of side L, we have a triangle of side L, this is an equilateral triangle, then its center will be at a height, suppose x, this angle will be 30 degree, this is x cot 30, and x cot 30 is again L by 2. So this length is L, this is half of that. So L by 2 is x cot 30. So x is L by 2 root 3. So this is x in this triangle. Here we have a by 2 here. So therefore this much of distance will be, in place of L we have a by 2, so a by 4 root 3. And similarly for this triangle we'll have same distance. This distance will also be equal to the same value. So the total R is twice of this, which we have to put here. So it is m a by 2 root 3 whole square over 4 plus I0 by 16, and let's solve it and see what we get. I0 minus I0 by 16 minus I0, 3 I0 by 16 is 3m over 4a square upon 12. So 16 minus 1 minus 3. So 12 I0 by 16 is 3ma square upon 4 into 12. Okay, so cancel. 4, 3 times 4, 4 times 4 and 4 go. So I0 is 3 and 3, they got ma square by 12. So this is the moment of inertia of this triangle about its center. Okay, so this is the method we can apply everywhere where we have subparts of same shape.